then investors will choose to invest in the market portfolio because that's maximizing the returns. That's number one. Okay. And then when we want to find this portfolio, then we go back to what Ibn has told you, that this is the tangency line. Right? So when you have the security market line, which is the regression line, and when it is tangent to the efficient frontier, then that tangency point is the, well, gives you the ratings as they have it here. So that's sort of, that's the capital allocation line, CML. And then sort of, well, this CAL is also called the capital market line. So that's the line where you do, you can do the optimal invest. Right? So that's sort of what we have. Two very small implications which you know. Right? Well, of course, then when it comes to the estimation, because we have this basically framework, right, then you have beta, and beta I, we sort of know what it is, that's risk exposure. So you have the sort of, that's the pricing equation and expected value. You have the risk-free rate, which we sort of understand it. So in this risk-free rate, then there are some components like this. Right? So how sensitive the returns are with respect to the portfolio, and risk, and so on and so forth. Right? So that is sort of the, well, that is something that we talked about the other day. That, well, CAPM actually tells us that investors are rewarded for bearing risk, systematic risk, not systemic risk, but systematic risk. And then, well, that sort of the risk that you have is somehow, well, this beta indeed tells us how much are we going to be rewarded. Right? So that's the reward that you get for bearing some part of the risk in the market. Right? So that's sort of what we have. And that's measured by beta. When you understand that, I don't need to talk about this too much. And of course, beta being one, then the asset is as much risky as the market. And if it is smaller, then it's less risky or more risky. All right, that's sort of what we have here. All right. And then, well, in general, the CAPM equation looks like that. That is what you know. But there is an alpha. Right? So that is the CAPM alpha that you have. And then if alpha is positive, then it means, well, that you have an intercept which is higher than the risk-free rate. So you are above the security market line. Well, it means that you generate more returns. When you take, well, that's what you are rewarded for. If alpha is positive, then you are actually getting more rewards compared to what you should. If alpha is 0, then you don't get more rewards, but if it is positive, then you get more. Right? So alpha is indeed a parameter. Well, I mean, there is this sort of large literature like hunting for positive alpha. So how do you find a fund manager that is capable of putting together a portfolio so that the alpha is positive? Right? And well, of course, so alpha being positive is interesting. All right. And then if some portfolio manager is capable of finding this, all right. So let's see. Let's go a little further. Well, let's say you estimate you have some portfolio manager or portfolio performance. You want to basically calculate how good a portfolio manager was. And you can calculate this alpha. Right? So that is what we have, which is also called the Jensen's alpha. Right? So that you have heard too. And then in terms of portfolio performance measures, then you have the Sharpe ratio or the framework which I told you the other day. So that you are sort of when it comes to analyzing the behavior of portfolio managers, and you can look at the Sharpe ratio, trainers, or sort of and CAPM alpha. It should be recording. Alright. So well, indeed, so it looks like that this CAPM is also interesting. Alright. So well, you can check the performance of people. Alright. You can also when you focus on CAPM beta, that's a very simple measure of systematic risk. Right? So if you have a portfolio manager, then you can estimate betas, and then you would know, right? So well, if you choose those portfolios with higher beta, then you are going to invest in more risky risky ones. If beta is smaller, then the portfolio will be essentially comprising the stuff that they have less risk exposure to beta. So that could serve as a screening, a very brief, rough screening for which assets to focus on. So that's the beta itself. And then some other basic stuff. But what I want to do is, I want to go, well, if kappa is good, alpha is interesting, beta too. So you can rely on alpha and beta if it holds in the given market. So you have to check whether it holds. And then if you check whether it holds, then that sort of opens some ways of doing research even now. So let's see the standard procedure, which is the Pharma Macbeth. This is in the paper which I just told you. So let's say we have the CAPM equation for acid I that looks like so. Right? That's the regression, which is a model for the expected value. The CAPM regression talks about the averages before the test, and then you have to make some assumptions. For example, you say, all right, so I have the returns, and then I decompose like that so that you can run a regression. So that's an assumption. Whether this is indeed a good assumption or not, that's a different question. All right. But let's say that we have this. And here, when we run this regression, then we always assume that these alpha beta are not time varying. That's an assumption which is violated often. But let's assume that it is correct. But let's say that these alpha beta are not time varying. If they are not, let's say, so if they are not time varying, here we have RIT minus RF, well, it could be also time varying, equals alpha I plus beta I, RMT minus RFT plus shocks. Right, so these interacts. Alright, so that's sort of what we have for every asset this holds. Okay. So let's take an average of this across take an average of this equation, so that's for acid I. So if alpha I, beta I are not time varying, let's take an average, and you would have, well, averaging across R, then gives you this equation. R, well, that will be the average of asset return in the time frame that you have, minus the average of the risk-free rate. And then, so here you have something, like alpha. Well, let's write it. So here we will have R bar minus RF bar. Well, the average of this across time is alpha I. The average of this across time is beta I. It's not time varying. Times Rm bar minus RF bar plus epsilon R bar. So that's sort of what we have here. Well, that's an equation. Right? An equation across, indeed, across I. Right? Well, I mean, here we can estimate alpha I and beta I. So we can estimate from this regression on time both of the alpha and beta. We can do the estimate. So I do have. Now let's do what sort of something very unethical. Let's run such a regression. So then let's call this yi. And then I regress yi on a constant. So here I get gamma 0. And plus gamma 1 times beta some error term, U1. So the regression that I'm doing is not, well, I mean, beta as I get, right? And I run this regression. Alright, so regression of the averages across time of all of the assets. Rather, let's say we have I equals 1 up to n, so I choose n assets. For each of them, I estimate alpha beta. And then the average of assets, I regress on the coefficients that I estimated in the first regression. Alright. What do you expect for this gamma to be? What should gamma 1 have to be? Exactly. So that would be, you estimate this to be that. Well, so you expect this coefficient that you get here to be this one, if kappa holds. If it doesn't hold, then all these manipulations will be wrong. Alright? There's number one. And then for gamma 0, well, then this is a null hypothesis. Alright, so which is somehow, if kappa holds, potentially then this will be in this holds. Right? So that is one, null hypothesis. So if it is rejected, then probably something is wrong. Right? Either you have time variation, or maybe say kappa itself does something. So the equation we started with doesn't hold. So we can use it for screening, we can use it for pricing, we can use it for estimating alphas, and so on and so on. But the other implication that we have here is that, with another null hypothesis, that, well, I mean, some assets may have a little bit higher alpha, some may have a smaller alpha, negative positive, and so on and so forth. And then this is the constant of the regression, so sort of should estimate the average of alpha across all of the assets. So here you should expect this gamma 0 to be also 0. You should reject this. That's right. You should not reject. And gamma 0 should be 0, right? And so one of the kappa implications that we have. So gamma 0 should be 0, and gamma 1 should be like that. We can test for these. If they are rejected, then you would sort of doubt that kappa actually holds. Let's do it. So for that, then the class now becomes a negative name rather than again a workshop. So let's do that in Vietnam. And I don't need to help me get the Vietnamese components. Can you? Please, you are experts. All of you. Come on. All right. So, well, I need monthly data. So we've tested on a monthly series. On the VN index components. All right. So here what we want to do is, well, Tableau is about a market. Right? Now Vietnam has its own market. Right? So we have a market. All right. And then, so here we have the VN index, right? So that's the Vietnamese market index, right? Yeah. Right, so VN index. So that is something we need to have. We will be estimate. So that's the market index. And then this has components, right? What are the components? Say R1 and so on and so forth, also Rn. Right, so we need all of them. Well, not all of them. How many are there? There are 30. This is actually assets which we put together in, well, then we make the index. For example, S&P 500 has 500 for 3 components, right? That's the market index. So here we have EN index, and I want that we go and then find the data for the components of this EN index. So then will be the regressions, we want to round them, get the alpha beta, take averages on the second regression, and then the start test. Yeah. Are you willing to do that?
Yeah, research for that.
Okay, very nice. So then, let me be fun. So you know whether kappa holds for you. Because I can't do this. your laptop to this, and then we do it on your laptop. So you do the programming, I sit next to you. And well, I'm not going anywhere, so we'll be there to do regressions. You can do it and to put a dress on what you call. So the task is clear, right? So we want to get the components of the Vietnamese index. Well, I mean, how many there are, say 30, 40, whatever. All right. Run their regressions. Okay. Well, let's say we take 5 years of data, or maybe longer, if you have. We can also do it in a rolling window, but let's just start at well, after COVID. Well, 5 years is okay, or 6. Try to actually 60 there. Well, we can try.
have to pay for it.
Yes.
Alright. Well, then let's do it with the S&P 500.
Yeah.
That's sort of the template for Vietnam, just to know.
Did you do that with the previous cohort to test the campaign?
Yeah, I did the same, and I think Trump, the data science like yourself, he got the data,
Oh.
so, but I don't find it. I don't know where he sent me this stuff, but somehow I don't have it anymore. He found it, so we did it. So maybe I'm getting his name wrong. So let me just check. So it existed. Okay. If you don't find them, then let's do the S&P 500. But that would be a nice exercise for you. I just wanted that it's somehow something Vietnamese, but if it doesn't work, then all right, let's go. So I will do it, okay? And then so that you can take it for your stuff. So let's see where the data are. I have them downloads. Alright. This is the CAPM data. Okay. So we just look at it, and we have done it already. So here then we have the S&P 500 monthly. Alright, so that's the monthly data. Okay. And what? I mean, that's the index, and these are all of the components.
That's good. Now we're not doing work with the monthly, well, so far we did everything with the daily, with the stuff that we did so far. Now we'll go with the monthly, so we check this, whether this CAPM actually holds in the monthly setup.
And these are 10 years of data. You can focus on the last 5 years, all of the data, so that's sort of we are free to do. Now, so here, when some time ago we did this stuff, right? So with the MPT, so let's go to the MPT day 7 where we read the data, but here I will not do the daily one, but rather the monthly. Okay. Sometime ago we also did, that is the Farmer French monthly one. Alright, so it doesn't matter. So let's go to, well, this, alright, the 5 where we did the so here we did the MPT with 100 assets yesterday, alright. So we take that and go and do the exercise of the day. Alright, so far so good. So that is what we have. So instead of daily, then I will have the monthly sheet. That is this. Alright, so I will have the and we can read them, we don't read it out. So these are everything that we have done previously, so we just run. these are, well, I mean, they are the monthly prices.
Could you do that? Should maybe arrange for you so that you copy paste from the previous code, and you can program. Alright, so this is where we did yesterday we did the investment exercise with the 100 assets. So we took the same program, alright, where it's going to read the month values. So instead of daily, then I'm getting the monthly ones. And then the rest is the same, so the prices and so on and so forth. Right? So that is what I call. Ready? Well, returns we will calculate later, so now I have not yet done. You can also do the return calculation if you are there.
So you're using the monthly data, you need to change the date.
No, well, that's simply a date.
Okay, just leave it.
Yeah, the only thing you need to change is from daily that you change to month. So then the sheet. The sheet was a daily sheet. Alright. Now we go read the monthly. Alright, so then this is the data, right, so which you have online. And then previously we were reading the daily, now I'm reading the month. And then the date is, then it was called the start date, but now it will be called date. So that's no change, just a month.
So now we need a risk-free rate. We would want to do calendar. So let's get the risk-free rate. When I mean risk-free rate, so here then we have I will use the 3 months treasury bill, secondary market rate, frequency monthly. Alright. And the ticker is TB3MS. So that's treasury bill 3 months series. Alright. So I just need this ticker. Alright. Now I will go back to my program. So here I want to get the risk free rate. We use a short rate. Short, not 10 years, but I'm using 3 months. Okay, so let's get a start date. The start date will be df.index.mean. So that's the beginning. So just give me returns. Alright, so that's the beginning. And then we need an end date, which is the max. So sort of the beginning and the end so that we have the max dates. Now I need the RF series. Alright, so here let's bring the pandas data reader. Import, or let's say from pandas data reader. Right? And import data as well. Right? So that is what we need to connect to Fed. Right? So that is what I did. So just bring the pandas from the pandas data reader, the web, the data section, which helps me connect to Fed, bring data. It looks like so. But that is something we also did before. But I got the daily T-bills, so here I will get the monthly one, exactly the same. So let's go on and we'll start reading we're connecting to the Fed. So here I would say so that is going to be the web. So here web has a data reader. I think it also has the get first data. So that's the one. The get first data. Says okay, what is the symbol? Alright, so that is TB3 months. Okay. Then we need a start date. Start, which is the start date. So needs an end, which is the end date. And well, let's just see how it works. Start date is not defined. Fair enough. Great. Then I have this series. So they start from 1st of March, alright, and then they go to whatever. Alright, so that is what in the very end. Right, so now there is a mismatch in terms of the dates, okay? Well, let's look at them. So the return series that I have, that's end of the months. Alright, so here we have the beginning of the months. So that's the 1st of March. And this 1st of March should be matched with the end of February. Alright, so that's sort of a little maybe problematic. Right? So, and then let's look at the end. Alright, so the end of the returns. That's 31st of March. Alright, 25. And this is 1st of March, 25. Alright, so 1st of March, 25. In the risk-free series, then it will be end of this. Alright, so here then I need one more month. So that the data can match. Understood?
Can you say that?
Of course.
Look, these are the return series. Alright, let's look at the beginning of the return series. And these are actually very important software stuff. And you work the data so you get indeed the results correct. Look, the return series that I have, they are end of the months returns. So that is sort of more or less the 1st of March. Alright. So here the Fed data, well, tells me the beginning. Alright. So what I will do is then I will match this with that series in terms of the index. Okay. But when I downloaded this, then I also noticed, directly noticed something, some other difference in the dates. And that's why I looked at the dates. Because I want to merge them. Whenever you want to merge data frames, you always look at what is happening. Look, I mean, the return series, 134 data points, but the RF series are 133. Right?
Yeah.
Because the end is at the beginning is the end, so somehow, well, things went wrong. Right? So what I want to do is, I will match the beginning of these two together, right? So to speak, well, this has 134 data points, this has 133. So if I match the beginning with this, the first with the first, second with the second, then I will come to 133, and then 133 here. And then here I will have 134, but no 134 there. So I will generate, well, I will now connect and then produce one more series, one more data point for the other one. So the length will be the same, then I can now go on and then make the indices the same. So
have the end date of the return series, right? That's March, right? And that is the end date. And the end date is 31st of March 2025. Alright? So here, then I will take that and then replace this with this value. And then here I would say 4. Date time is not there, so we have to import it. So the end date I've changed. Then we go here, import date. Okay? Now I have that, and I will run this thing. Why it doesn't read more? Fine. Oh, now it's one more. Wait a
Because
moment.
they only,
April doesn't?
yeah,
work?
it's 30 years.
Okay, now it's good. Okay, now I can match. So to do the match, then that would be great. So because I looked at these dates and I know that they are not problematic, then here the index I will set to returns index. Now let's look at these. Alright, so these are beautiful days. And they are the same as this. Okay. Now we can go. So here I just, because I looked at the indices, then I don't need to do more stuff. I just replace one index with the other, and we are good. We can merge them or not merge them. Doesn't matter now. So in terms of plotting, I think we Alright, so far so good. Now we can start with doing well. And these are monthly rates, but they are reported for yearly returns.
This 5% should be divided by 12. So these are, they are monthly TVs, but the values that are reported here are yearly returns. So that's 5% in a year. So we have to divide this by 12, so this becomes 1. And when we do our calculations.
Right.
It took us some minutes to get these, get those, now we can run our equations.
So the exponential variable for all of these variables is the same. Right? So that's the market index minus the risk-free rate. Right? So we can we generate the x variable. Right? So here we would say x is equal to returns, and that is called SPX. Unweighted equity, so that is my x. SPX just index, that's right. For the others, then we have the, so that's my x, I'm happy with. Now we need voice. The voice change, right? So of course, then this is minus the RF series at the T-bill 3 months. So that's our x. Now let's generate, now let's go and then do vice. Alright?
Now, the thing is that you have to be careful with the program, of course, right? So here, in the first regression, so this is the first regression, right? Then we get the cap m alphas, we don't need them for the next one, but we need the cap m betas, so these coefficients we need. So if I run all of the components, right, so say 100 of these assets, if I run them one by one, then I need these betas to I also need these averages, right? So, well, when I run this regression, then I need an average of the dependent variable. So that I should also collect, because later that will sort of serves for me as the dependent variable. I will collect this, I will collect that, right? And then we can go on. So what I can also do here, so this one, well, that's the idiosyncratic error. I will also get the residuals here, and then get their variance. I will keep it too. Alright, I want to know what happens here. You will see that's useful in a minute. So this epsilon t is indeed a shock, which is not systematic. Right? So that's not part of the systematic variation, right? So that is something which shouldn't be priced. CAPM doesn't pay you for the unsystematic shocks. What tells you that you will be rewarded for the systematic part, right? That's where beta is, right? But that is something that I will keep, right? Because CAPM tells me that the shock, the variance that you have there, shouldn't matter. Right? So I will keep it for that.
This is the start. Let's do assets, and assets I will take as these are all, so returns dot columns, but I will do not all, so first should go out till 120. So that is what we did like yesterday. I'm not looking at all of the assets, but rather just 100. Wow. So that's sort of what we have. So these are the assets. Right? Now, well, I set n for my CAPM testing to 100. Right? Now we go on. So for I in a range of n of assets, then do the following. Get me a y. Right? So y, that's the dependent variable. That will be the returns of this TB should be divided by 12, right? So 4 rows. So that's monthly. So now I go in assets, in returns, go to assets number I, right? And subtract the TB off. So that will be the minus this term. Alright, so that is what we have. Now we can run our regression. Alright, that is what we have. It should work. Right? And the regression that we have, well, let's call it results. Alright, so that will be sm.s. Endogenous variable is yi. Exogenous variable is sm.add a constant of x, then we do a fit, and then we need beta. So let's collect betas, right? So let's say this is beta, that's a list that's empty, alright? We get the averages of average I, so let's put average I, that's also empty. Sig I or sig 2I, right? So that's also a list because I want to collect it, right? Does it make sense?
Yeah.
Okay. And now we can go on, right? So to beta, we append what? We append from the result, the params, we need an Euler 1. So that is beta. To average I, so that's the dependent variable, we also append something. And that is what? The average of y. So here we have in P, what is it? Tell me, of yi. I don't remember. I hope that it works. Somehow seems okay. Alright, then we need sig 2I, so that's the variance. And then here we need an NP var of result. We need the residuals. There are
program this regression for 100 assets. So we got these beta R's, we got these averages, now we can do this. So we will regress now the averages and beta plus the constant. Then test whether this constant is zero. Then we do the first. But let me give you time, so let me time. Average on, these are the averages. So these are the mean of lines.
Oh, okay, yeah, that's what you call it. To be fair, 1 second, for sure.
So yesterday you told me that you sort of tell me, oh, this is so interesting that I can program without ChatGPT. And because I remember what I need.
Oh.
I need it. That's my regression. I don't care about those, but I care about what I need for later. Correct. That's important. I made mistakes, of course. That's why you're here. So let's run the second stage regression. Second stage regression. And then we do, let's call it second. And that is the end of let's be from the first stage. So first stage, then we need the AVGI. And then the X is the same constant of first stage beta. I'll make it a bit smaller. Or now we do a dog fit. We set the proof type to HC. And now print second result. So do you reject Kaplan? Does Kaplan hold? Let's do this with 200. Just so what? in a lower boundary value classes.
Uh,
Yeah, potential. So whether it's somewhat different, or potentially there has been some other time. But I mean, the thing is that we shouldn't be negative. If it is, well, if it is zero, then maybe it should be positive, right? So, and we believe that it doesn't hold. Right? So that's sort of, that's what it tells you.
I mean, the gamma one is negative, it's zero.
The gamma one is also negative, that's true, it's also here. Right?
Yeah.
So we can, I mean, what we need is to test the other one, right? So that is, that if this coefficient, right? So we want to test whether this coefficient is the same as this average. So we need this x, so the average of this x. Right? And then how do we test for it? Then we put together, well, this is for testing for the gamma one switch. So that is what we are. Then we need the T statistic, right? So here the T stat becomes second dot params. So we need the parameter. We say that this is an R log. Wait a moment. The testing, but that's much a econometrics question. So can I take this p-value for this node? No. Because that is for the node that gamma 1, or so this is testing whether beta is 0.
Ah, yeah.
And that's the T statistic. So we have to make up the T statistic on our own.
Ah, yeah.
So that would be, well, I mean, that's the parameter in location 1 minus np dot mu of x. So we call it the x. Alright, so that's the hypothesized value. And now we have to divide it by second dot params. No, it's called SE, right? SE dot I log of 1. Right, so that will be the T statistic, I believe. Maybe VS. Beta standard errors. I don't remember, so let's look. So, on VSE, I was close. I called SE and I got DS, so these are the details. So that's the T statistic. Let's look at the value. And let's select it. Right? Well, the value of the T statistic for this is that. So we reject this gone. This is rejected, this is rejected, and it is simplest for doesn't work. Doesn't hold. Alright? So this equation doesn't hold for you in this time period, 2014 till now. Okay? In some periods it may work, some periods not, but here it doesn't. Okay? Let's do some other regression. Okay. So the other regression that I want to do is I want to test whether some of things don't work out, right? So here I will include sigma 2, sig 2 also as another regress. So not only a regress on beta I, also regress on the variance. So that's the risk, which is not accounted for by condition on the market basis figure. So then let's run it. Well, obviously the coefficient on the sigma score should be 0 if Kaplan holds. Right? Well, so to speak, you shouldn't be paid for unsystematic risk, but you are. when you are paying. Not only those coefficients are problematic, they are not equal to, well, this is not zero, this is not sort of the same as this average, but the coefficient of sigma squared is also, oh, this is zero. Okay, sorry. So that's zero, so at least that part actually works. Alright. But I mean, we believe that it doesn't work, alright? So we require this, that gamma 0 to be 0, you require gamma 1 to be equal to this, and you require the coefficient of sigma squared to be 0. If it was not, then it would have meant that investors are paid for bearing the unsystematic risk. Alright? Somehow they bear it. Sure. Well, that was a sort of a question of my own, right? I was thinking, so that's how I think. That I have cap M. And cap M actually tells me that when you bear some risk, because you buy this, then we pay you. Well, sort of, you get some returns. And the return is somehow associated with how much risk you have here in the market. Right? So how much risk you have, I mean, beta. So beta is the risk exposure. So if this goes a lot high, then you get, and if it is a positive, then you get more returns. Right? If it goes a lot down, then sort of you don't get as much. Right? That's sort of what beta is. So beta seems to quantify sort of prices, or you can think of it as a price. Right? Some premium that you're paying essentially. Later on with returns. But you're not paid for everything else. Right? So this shouldn't actually, so you bear some risk from the market, which is the systematic risk that is here. So what we have there, there's also some part of the risk that you have, but that is unsystematic. And then the unsystematic risk is something which you shouldn't get paid for. Right? So it's somehow too random. Sometimes that's sort of a reward for a shock. Right? A reward. You are not rewarded for a shock, right? Which is not here. Right? So to speak, this I took, right? And calculated its a standard what, sort of a variance. So that's the unsystematic risk. And CAPM tells me that you shouldn't be paid for it. And no. So that's something that at least holds at situations. But all in all, CAPM doesn't hold its simplest form. Okay. Now 5 minutes we have. Now all of everything that I did here will start with the assumption that these are not time varying. Alright, maybe they are time varying. Actually, I'm rejecting CAPM holding, not because CAPM really doesn't hold, but because I'm testing it in the wrong manner. So they're starting with the wrong model. So that alpha beta are time varying. If they are, then this equation will not hold. Alright? That's maybe. We don't know. Alright? Maybe it can very holds. But because they are taking a wrong approach, then things don't work. Okay? That's number one. So number two is that, so here the individual sort of this basic guide that we have. So here we took an average, this we call yi, and there is this estimated in the curve, so there is a generated regressor. These are not real variables, these are some things which we estimate. So our regressor is not a perfect regressor, right, but it's a generated regressor. And it brings in some problem with it. Because this risk, it has some bias provided. It has some estimation error. Right? So it's not a precise estimator. And then this estimator being not precise, not a real one, actually affects the standard errors. Right? So the the standard errors are not true because I'm working with an imperfect basically variable. It has measurement error. Yeah, remember that we had measurement error issues from bachelor statistics. So that's another issue to keep in mind. And maybe one can improve on this procedure. And then the other thing is that so here the regression that we got here, right, indeed has all of the shocks. So that's sort of where that's in I, right? But then, so here we are treating this as being independent from betas, right? Mean use, which are the average of the individual shocks, to be exogenous with respect to the independent variable. So that is the independent variable. Maybe it is not. Maybe they have actually some problems. Right? Maybe there is some dependencies here. Such that this is indeed somehow not really sound from an information point of view. Right? But that's a standard procedure most of the people take. Right? It has flaws. It can be improved upon by taking into account the potential time variation that we have, by taking into account that this guy is a generated regressor, so the standard error should be refined. Maybe the standard errors are small, really, in reality, but they are not. So we didn't do this. We simply took them as variables and then we run the regression. And then this error time is also being an average causes the issues. Right? So, all in all, these standard errors may be wrong. Alright. So one should refine them. Okay. So that's as I said, that's a procedure that most of the people may use to test for CAPM. But that's not the best one. Alright. Maybe there are non-linearities. So maybe that's a non-linear function. Maybe we take this to the power of 2 and break it in the regression 2, say. And so on and so forth. Alright. So I gave you a bit of a review of what is CAPM, how could one derive it from different basic aspects, and then I gave you a testing procedure. Right? That's more academic, right? In the sense that, well, if you want to use CAPM, then be careful with it, with the screening, right? Because it may not hold. And of course, then one of the reasons it may not hold is that you need more regressors, so then we have the factor models, which we discussed the other day. Right? You need more variables so that you reduce the variable bias, and so on and so forth. And with that way, then things may be a little better. Right? Well, so far so good. I think I'm done with this part here. The time is also over. Today in the afternoon we don't have any sessions, but tomorrow we do. Tomorrow we continue the factor models. I told you, I don't have a lot of the slides on that. But there are historical accounts. Why do we need them compared to the account that I think I told you before? So maybe tomorrow I can do principal concordance. Which I know you have potentially learned before, so we'll refresh you on the theory and then tell you how we implement them in practice. That will be tomorrow's session. On the last day, then I will do the exercises, which are posted online. We didn't maybe have time. We were busy with other projects and so on and so forth. We couldn't go through all of them, so I will come and review.
All of those?
Assignments. Not all, but some.
Okay.
Let's see how much we do. Okay? And then that will basically bring us to an end of this class. Thank you very much for your attention.